Conditional probability is involved with the multiplication rule. The notation for conditional probability is the probability of B given A. So this is a straight up and down line. So as I said, it's the probability of event B, these are events that we're talking about, of B, given A has occurred. Okay, what's the probability of B happening given that we already know A has occurred? Now, probability involves a condition called independence. Two events are independent if the occurrence of one does not affect the probability of the occurrence of the other. So two events are independent if the occurrence of one does not affect the probability of the occurrence of the other. Thus, they would be independent. So when we think of the example we saw with the balls in the urn, and we were selecting two balls from the urn one at a time, once we drew the first ball out, if we put it back in, then the probability on our next draw is not affected by the first withdrawal from the urn, because we're back to the beginning. The urn is just as it was before the first draw if you replace that first ball. So they would be independent. However, as we saw with our example with the urn, if you do not put the ball back in the urn, then there is a change in the probability. It is affected on the second draw by the fact that you have done the first. So what I'm saying is, when a procedure is with replacement, we have independent events. If the procedure is without replacement, we say we have dependent events. So our multiplication rule is written the probability, remember this is A and B, the word and indicates multiplication rule, is equal to the probability of A, that's our first draw, right, times the probability of B given that A has already occurred. So if they are independent, the probability of B given A has occurred is the same thing as the probability of B. If they are dependent events, then we do make an adjustment for this condition. So returning to that example we had of the urn, and we wanted the probability of red and white, we would say, well, that's the probability that the first one is red times the probability that the second one was white, given that the first one was red. And remember, when our situation was dependent events, what we saw was there were 3 reds, so the probability of red was 3 reds out of 12 balls in the urn, times the probability of white. Well, there's still 5 white balls in the urn, but now what has changed is there are only 11 balls total in the urn. So that's the probability of B, given that A has already occurred. When A occurred, one of these balls was taken out and set aside. And that's where we got that answer of 0.1136. Okay? This was our case. I think we called it, well, I don't think we labeled them, but that was the second case where we just mentioned that it was without replacement. Now, with replacement, again, if events are independent, then our multiplication rule is the probability of A and B is equal to the probability of A times the probability of B. Only if they are independent events, because B has not been affected by A. This works for both because you'll take that into consideration, but I'll make a note here that this is specifically used for dependent events, okay, or without replacement. So let's summarize what we're saying here about independence. I'll just call this an independence summary. Okay, so these statements are equivalent, the statements I'm about to write. First, A and B are independent events. Well, if that's true, that's the same thing as saying the probability of A and B is equal to the probability of A times the probability of B. That's the same thing as saying that they're independent events. Well, why can we say that? Well, because the probability of A given B is the same thing as the probability of A, and the probability of B given A is the same thing as the probability of B. Okay, don't mix these up. It does matter what order those are in. The probability that A occurs given that B has already occurred, or the probability that B occurs given that A has already occurred. And you can see how they are written based on independent events. That's what we're saying. Recall, that's what we were saying previously, that if they are independent events, the probability of A given B is the same thing as probability of A. If they are independent events, the probability of B given A is the same thing as the probability of B. So that's our case when we return the ball to the urn after that first draw. So it makes no difference. It's not changing the outcome or the probability of B occurring. So these events would be independent. There's no condition of dependence there.